Hello everyone, my name is Leandro Novaki. I'll be presenting João Vitor's and mine studies under the Professor Dr. Frederic Grassi. In this poster, we'll be discussing our studies over hydrodynamical models with the smoothed particle hydrodynamics simulation method, or SPH as we call it. The SPH method is a Lagrangian method that discretizes the fluid as interpolating particles, which move with their own velocity and acceleration. With the SPH method, we translate the fluid equations of motion into the equations of motion for the SPH particles. This gives us the advantage of automatically conserving physical quantities, such as mass and energy. To achieve this smoothing, we use the so-called kernel function W, that approximates the Dirac delta function by a length parameter h, or smoothing length. In particular, we use the spline interpolations in our works. The proposition of the method is to calculate a single quantity from a particle by weighting the contribution according to the density and the smoothing length parameter. Another advantage of this calculation of arbitrary quantities is that the derivative is calculated only over the kernel, which is also known. We focused on the classical version of the Euler equation and the conservation equation associated with the fluid, using the equation to calculate arbitrary quantities to rewrite the density and the pressure. We are then able to develop the differential equation of motion for the SPH particles, which is displayed on the screen right now. With numerical methods such as Runge-Kutta and Leapfrog, we can then advance in time and follow the position and velocity of each SPH particle. We then can calculate the density with the equation for an arbitrary quantity and the pressure by the thermodynamical relation for a polytropic fluid. The model we use to test the SPH method is called classical simple wave, or classical tube, which is a one-dimensional fluid expanding on vacuum, as we can see on the image displayed right now. The initial condition is an equilibrium state where the fluid fills the tube for negative values of x, where we set the equilibrium density, and we set the velocity of the particles at 0. In the following simulation presented, we use these quantities as our constants. We use 6,000 number of particles, a 15 total mass of the fluid, a smoothing length of 0.04 divided by square root of the number of the particles divided by 1,000. Our timestamp is 0.04, the constant of the equation of state is k equal to 0.1, and the polytropic index is 1. This is the mass density profile normalized and presented in different timestamps, where the dotted line is the results of our simulations. Of course, looking at this image, we can't really analyze how good the approximation is. Of course, the dotted line seems very close to the rigid line, but we can have a better grasp of the quality if we see the error graphs. This is the graph of the error of the density SPH simulation when compared to the analytic equation. From these timestamps, we can analyze the error quality, and indeed we can see the density calculation via SPH as a good approximation, since the order of the error is much smaller than 1, especially on the intermediate timestamps where the fluid has not developed much. This graph displays this in the most visual way, which is the graph of the error in function of time. The problem in the initial timestamps is that the particles have yet to arrange themselves as they should. And the problem in the end is because a lot of the particles at the border have a higher distance between, and with so there is less information for the smoothing to be accurate. This is the velocity profile for the same timestamps, with the dotted line also representing the simulation data. It's important to mention that the decay of the velocity simulated profile happens because of the way the method works. The border region doesn't have many particles, so the contribution tends to 0 as we distance ourselves from the region where the classical tube is well described. We decided not to display the error analysis because of this problem, where the error would obviously be much higher. In retrospect, we could see that the SPH method works well on describing classical fluids despite the divergences near the boundaries. In our attempts to get better results, we use gross particles and a time-dependent smoothing length, which decrease the inconsistency on near the vacuum boundary. As for the next steps, we will learn new methods to improve our results and different theoretical methods so that we can put the SPH method to test again. Now, I want to thank everybody that attended to this presentation. Me and João Vitor want also to give our best acknowledgements to our supervisor, Frederic Grassi, and to our research group, which have been both very helpful and available in all our work.